Okay, so now we are ready to talk about entanglement, which plays a central role in quantum computation. So let's come back to a 2-qubit system, and which, let's say, again consists of atomic qubits, where our first qubit happens to be in the state superposition alpha 00 plus alpha 11. And the second qubit happens to be in this superposition beta 00 plus beta 11. So now we could ask, what's the state of the 2-qubit system? Well, the answer is very simple. What you do is you just take a product of these according to this rule. It's sort of the obvious rule. So the amplitude of 0, 0 is just alpha 0 times beta 0. The amplitude of 0, 1 is just alpha 0 times beta 1. The amplitude of 1, 0 is alpha 1 times beta 0. And the amplitude of 1, 1 is just alpha 1 beta 1. So for example, suppose the states of the 2 qubits were, the first one was in the plus state, and the second one happened to be in the state minus 3 over square root 3 over 2, sorry. Then the composite state, the composite system is in the state, well, 1 over 2 square root 2, 0, 0, minus square root 3 over 2 square root 2, 0, 1, plus 1 over 2 square root 2, 1, 0, minus square root 3 over 2 square root 2, 1, 1. Okay, so that's quite simple. Okay, so now we could ask the opposite question. So suppose you are given the state of the composite system. Determine the state of each of the 2 qubits. So we could just continue with our previous example. Suppose you're given that the state of the composite system is this. Okay, so you're given the state of this system. Now you want to determine what's the state of each qubit. How would you do that? Well, the answer is clear. What you would do is you take the state and you would factor it in the form alpha 0, 0 plus alpha 1, 1 times beta 0, 0 plus beta 1, 1. And this factorization may not be unique, but we don't care about the overall phases. And so, for example, in this previous case, what we could do is we could factorize it as 1 over square root 2, 0 plus 1 over square root 2, 1 times 1 over 2, 0 minus square root 3 over 2, 1. And we could say that's the state of the first system. Now, of course, we could also, this product will remain the same if we apply a minus sign to this and apply a minus sign to that. So in other words, we could make this state be minus this minus that, and we could make this state be minus this plus that. And the product of these two would still be the same. In fact, we could apply any phase here and the opposite phase here, and the product would still be the same. The phases, as long as the phases cancel. But of course, the overall phase of a qubit doesn't matter, so we don't really care about that phase information. What we care about is understanding what's the state of each qubit up to a phase. So now we could ask, given an arbitrary such state of the composite system, can you always factorize it in this way? And the answer is no. There are states which you cannot factorize in this way. And these are the so-called entangled states of two qubits. This is quite surprising. The reason is that a state that you could not factorize, for such a state, each of the two qubits, the first qubit and the second qubit by itself, is not in a definite state. It does not have a quantum state. All we can say is that the composite system is in some quantum state. It's in some superposition. But if you look at just the first qubit by itself, it's not in any given quantum state. The way we describe it is it's entangled with the other qubit. The two qubits are completely entangled with each other to the point where neither of them has an identity of its own. So let's see an example. So a canonical example of entanglement, of two qubit entanglement, is the Bell state. So it's this very simple state. It's a equal superposition of 0, 0 and 1, 1. So the claim is that if the two qubits are in this joint state, they are completely entangled with each other to the point where you cannot really talk about what the state of each qubit individually is. So why is that? Well, let's try to factorize this. Let's try to write this as alpha 0, 0 plus alpha 1, 1. So let's try to factorize it. Times beta 0, 0 plus beta 1, 1. And let's show that no such complex amplitudes, alpha 0, alpha 1, beta 0, beta 1, exist. So why is that? Well, we know that the amplitude of 0, 0 is the product of this and this. So alpha 0 times beta 0 is equal to 1 over square root 2. We also know that 1, 1's amplitude is alpha 1 times beta 1 equal to 1 over square root 2. What these two facts imply that alpha 0, beta 0, alpha 1, beta 1, they're all non-zero. Okay, but now let's go back and look at the fact that what's the amplitude of 0, 1? Well, that's 0. And so what that means is that alpha 0 times beta 1 must be equal to 0. But that's not possible because what we said is that all four amplitudes have to be non-zero. So that's a contradiction. So what this shows is that we just cannot write this state, we cannot factor this state as a state of the first qubit and a state of the second qubit. Now, we are going to study the properties of this Bell state, this entangled state, over the course of the rest of this lecture and the next lecture. But for now, we are going to study what happens if you measure this Bell state. So imagine that you create this Bell state, and now you take these two qubits, these two particles, and you separate them by a great distance from each other. Well, of course, none of this affects the state of the particle, so the state of the particle is still 0, 0 plus 1, 1. What happens when you measure the first qubit? Well, when you measure the first qubit, you see 0 with probability, well, the square of the magnitude of this, which is a half. But what happens when if you actually happen to see a 0, measure a 0? Well, remember the rules of measurement? What they tell us is that if you see a 0, the new state is going to be determined like this. You just cross off the parts of the superposition that are inconsistent with the measurement outcome, and you renormalize. So the new state is 0, 0. On the other hand, if you see a 1, you see that with probability a half, and the new state would be 1, 1. Now, what happens if after this you measure the second qubit? Well, the answer is clear. If you measure second qubit, well, in this case, you would see 0 with probability 1. And in this case, you would see 1 with probability 1. So it's as though, there's this strange coincidence between the two measurements of these two different particles, even though they might be arbitrarily far apart. Well, so far this is something that you should be able to reconcile with your intuition, because you could say, well, wouldn't you get exactly the same result if when these two particles were initially entangled, they flipped a coin to determine whether they were going to act as though they were in the state 0, 0, or they were going to act as though they were in the state 1, 1. And then once they are separated, they just happen to be in that state. It's as though you flipped a coin when you created the state. Well, it turns out that it's not so simple. And in the next video, we'll talk about the EPR paradox, or the Einstein-Podolsky-Rosen paradox, which shows you just how strange entanglement is.